Every ripple in water, every gust of wind, every swirl of cream in coffee. One idea ties it all together. Those are the Navier-Stokes equations, conservation of mass and momentum for fluids. They explain how the flow changes in time, how motion carries motion, how viscosity smooths it, and how pressure drives it. In this video, we are going to discuss conservation laws, conservation of mass, substantial derivatives, conservation of momentum, conservation of energy, transport equations, and at the end, we will discuss two simple flows, Couette Flow and Poiseuille flows. By the end, you will read a flow field like a map, and you know to spot what each term does. Let's start. To write governing equations for fluid flow and heat transfer, we need mathematical statements of conservation laws of physics. For Navier-Stokes equations, those laws are conservation of mass, conservation of momentum, second law of motion, indicating the rate of change of momentum of fluid particle equals sum of forces acting on it, and conservation of energy, that is first law of thermodynamics. The rate of change of energy of a fluid particle equals the rate of heat added plus net rate of work done by the fluid particle. Now, let's start with conservation of mass. To write conservation of mass, first we need a fluid element. Although this element must be small, it cannot be smaller than a specific size. Why? Because we want to disregard molecule structure and molecule motions of fluid, so that the properties of fluid like density, pressure, velocity, temperature, that they all could be functions of space and time, will not be affected by the amount of molecules entering or exiting the fluid element. Conservation of mass indicates rate of increase of mass in a fluid element equals net flow rate of mass into the fluid element through phases. Now, let's write it in a mathematical language. For mass, we use area, velocity, and density to have it in our equations. And we use Taylor's series, just the first two terms, because the element is so small. And we use Taylor's series to show the amount of mass entering or exiting our fluid elements. For the left-hand side of equation, rate of increase of mass in a fluid element, we have partial T, rho, delta x, delta y, delta z. And for the right-hand side, mass flow rate into the element, we have equation number 2. When we simplify equation number 1 and 2, we have partial T rho plus partial x rho u plus partial v rho v plus partial z rho w equals 0. And this is conservation of mass for a compressible fluid. Now, if we simplify it for an incompressible fluid, where density is constant, we have gradient dot u equals 0. Before we discuss conservation of momentum, there is another concept we like to talk about, and that's substantial derivative or total derivative. It is called dphi dt, and it says partial phi partial t plus partial phi partial x times partial x partial t plus partial phi partial y times partial y partial t plus partial phi partial z times partial z partial t equals dphi dt. And since a fluid particle follows the flow, we can redefine partial x partial t, partial y partial t, partial z partial t to u, v, w, our velocity components. And it simplifies to partial phi partial t plus partial phi partial x times u plus partial phi partial y times v plus partial phi partial z times w. And it simply shows a rate of change following fluid particle. Partial phi partial t indicates local rate of change, and u dot gradient phi shows convection term. dphi dt is in Lagrangian frame, while partial phi partial t plus u dot gradient phi is in your Eulerian frame. Let's look at it from another angle. We say local rate of increase of phi plus net flow of phi out of fluid element. When we write it down, it is like partial t rho phi plus gradient dot rho phi u. If we expand this equation, we have these terms, and when we simplify it, we have these two terms. We already said, based on conservation of math, this term is 0. So, one more time, our substantial derivative is written. Phi could be any property, u, v, w, momentum, or energy. And remember that it's per unit mass. So the equations that we wrote for conservation of mass and others, they were per unit volume. But phi is per unit mass. And in our future equations, we need to remember that and use the same unit. Let us continue with conservation of momentum. So the left-hand side of the equation, rate of increase of momentum for a fluid particle, can be divided to two terms: local rate, change of momentum for a fluid element, and net flow rate of momentum out of fluid element. And in mathematical terms, they are as shown for the three directions, x, y, z. Momentum equation indicates that the rate of change of momentum of a fluid particle, the equations we just saw, equals sum of forces acting on a particle. So we have two types of forces: surface forces that are viscous and pressure forces, and body forces like gravity, Coriolis, centrifugal, or electromagnetic. Body forces are usually treated as source term. Now, we like to write forces acting on fluid elements' surfaces in x direction. Now, we can simplify it. Some terms are cancelled, and we have this last equation, that is per unit volume. For y direction and z directions are accordingly, and if we put the right-hand side and left-hand side equal to each other, we have these equations for the three directions x, y, z. Now, up to now, we are discussing conservation of momentum. And we don't know stress terms. We do not know them. They are question marks for us. But when we model stress terms, then we have Navier-Stokes equations. So the difference between conservation of momentum and Navier-Stokes equations are in stress terms. In Navier-Stokes, we have models for stress terms, while conservation of momentum, we have no clue what the stress terms are. Conservation of energy says that the rate of increase of energy of fluid particle equals net rate of heat added to fluid particle plus net rate of work done on the fluid particle. Let's look at each term separately. First, we check work term. The net rate of work done equals surface and body forces times velocity. So we have forces acting on the surfaces of our fluid element and on its body. If we write these forces times velocity, for x direction we have, as you can see here, and if we write for y direction and z direction and simplify, we will have w dot equals minus gradient dot pu plus partial xj ui tau ij. And this is the work done on the particle. Now, let's look at heat transfer term. This heat transfer is conduction. Remember, on the left-hand side of the equation, we had convection. On the right-hand side, we have conduction. And as the others go, heat transfer is same. We can use Fourier's law to rewrite our equations. Heat transfer equals minus K gradient T. And when we replace it into the equation, we have gradient dot K gradient T. So the rate of change of energy equals work done plus heat transfer or heat added, which is minus gradient dot pu plus partial x ui tau ij plus gradient dot K gradient T plus S, that is source term. If we check all the equations that we have derived up to now, continuity, momentum, or heat transfer, we can see that they all have a similar form. Partial rho phi partial t plus gradient dot rho phi u equals gradient dot gamma gradient phi plus source term. So the first term is the rate of increase of phi. The second one is net rate of flow of phi out of fluid element. And on the right hand side, we have the diffusion term, net rate of increase of phi, and source term. So now if phi is equal to 1, we have conservation of mass. And if phi equals u, gamma is mu, then we have x component of Navier-Stokes equation. This equation is called general scalar transport equation, and it can be used for different properties. Phi could be temperature, enthalpy, internal energy, velocity, or K and epsilon, properties of turbulence models. To sum up, let's look at Navier-Stokes equation one more time. So here we have equations for a 3D incompressible flow. Since it's incompressible, it means density is constant. So density can be removed from the continuity equation, and we will have one equation showing that velocity changes in a continuum media. Then we have momentum equations for x, y, z directions. Partial t is the transient term. Then we have convection terms. On the other hand, we have diffusion term, and as you can see, we have a relation, we have an equation, we have a model for stress terms. So it's a Navier-Stokes equations. And at the end, pressure term and gravity term are our source terms. Let's look at two simple fluid flow problems. The first one is Couette flow. So this flow is defined as the flow between two planes, one fixed and the other one moving at u velocity. The assumptions are that the flow is steady state, incompressible, Newtonian, and laminar. And since our problem is a two-dimensional problem, we only have x and y directions. So we write Navier-Stokes equations that include continuity and momentum for x and y directions. Now, we know that there is no moving in the vertical direction. So v is 0, and we can conclude that partial u partial x is also 0, meaning that u is a function of y. Now, if we simplify x momentum and y momentum, some terms are cancelled, like the transient, because it's steady state. We already said partial u partial x is 0. We know that v is 0. So only minus partial p partial x and partial u squared partial y squared are left from x momentum. And from v momentum, we have minus partial p partial y plus rho g y. From v momentum, we have p equals rho g y plus fx. That is hydrostatic pressure, and it doesn't affect our problem, so we can put it aside. And from x momentum, we can reach to u equals 1 by 2 times mu partial p partial x y squared plus c1y plus c2. Now we use boundary conditions. What are the boundary conditions in our problem? So at u0 is 0, u at h is u. And when we input them into our equations, we get C1 and C2. So u can be defined as it's shown here. We also can calculate shear stress, and we can have shear stress at walls for both at h and at 0. So this flow, because of its simplicity, we are able to calculate it analytically. Most of the equations are not this simple, so we have to use numerical methods to solve them. But this is one of the exceptions. This is one of that we can solve analytically. The other flow is Poiseuille flow. Again, the assumptions are steady, fully developed, incompressible, Newtonian, and laminar. So this flow is similar to a flow in a pipe, or like in our blood vessels. It is pressure induced. So Couette flow is viscosity-induced flow, while Poiseuille flow is pressure-induced. When we write Navier-Stokes equations, and again cancelling terms, so since it's fully developed, gradients in x direction are 0. So we can see that partial v partial y is 0, meaning v is constant. And since v at the walls is 0, it means that v is 0 everywhere. Canceling terms for x momentum, we will be left with minus partial p partial x and mu partial u squared partial y squared. And for v, we are again left with minus partial p partial y and rho g y. Again, from the v momentum, we have hydrostatic pressure. We put it aside. Now, from x momentum, we have u equals 1 by 2 times mu partial p partial x y squared plus c1y plus c2. Now, boundary conditions here are different than a Couette flow. So here, both boundaries are 0. And we can achieve that C1 and C2 are equals. C1 equals to 0 and C2 equals minus 1 by 2 mu partial p partial x h. And we have U profile for Poiseuille flow. And we have shear wall for this problem too. Again, this problem can be solved analytically because of its simple conditions. And as we said, it's a pressure-driven flow. If this helped, don't forget to like, subscribe, and hit the notification bell so you won't miss our future videos. We also like to hear from you, so if you have suggestion, comment, or question, or you like us to cover some topics, leave a comment below. If you'd like to connect with us directly, you can use one of the links in the description box, including our website address. Feel free to reach anytime. Thanks for watching. See you in next video.